Okay, problem 11.1. Now we're given a function f. This is C1, and we try to update, find the minimizer of f by applying this iteration scheme. This alpha k is the step size, and then we use the steepest descent method such that the step size is the step size alpha k is the minimizer of this function with respect to the step size alpha. Okay, and we use the shorthand notation. The gk is the gradient of f at a point xk, and we assume that the dk, the descent direction, is the inner product of the descent direction dk and the gradient is negative. And want to show that in this case the dk will be a descent direction, meaning that you go along the direction dk, the function value will definitely decrease, at least initially it will decrease. And then we show that the step size alpha from the steep descent method will be greater than 0. Oh, by the way, the steep descent method I'm referring here is using this dk specific search direction dk, not necessarily the gradient. Okay, and we also need to show that the inner part of the dk is orthogonal to the gradient at the new point xk plus 1. If you use this alpha k as a step size, you reach to a new point xk plus 1. The gradient there is orthogonal to the search direction dk. And then we need to show that this property here, this inner product will be less than 0 for all the following four methods: the steep descent, which we use the negative gradient as the search direction, and the Newton's method, conjugate gradient method, and quasi-Newton's method. And finally, we suppose we have a quadratic function f, and it has a positive definite matrix Q as the quadratic term. Then we need to derive an expression for the alpha k such that it can be written in terms of this Q, dk, and gk. Okay, let's do these things one by one. So first, to show that dk is a descent direction, so we form the line search function. So now this function phi is a function of alpha. Alpha is the step size. Okay, so it's from R to R. It's from real number alpha to a real number. So we just need to show that the dk is a descent direction. We just need to show that the alpha, the phi prime at 0 is negative, right? Because this phi prime is a line search function. That means this is alpha. This is the phi of 0. So if we need to, go along this direction, we will actually track the function value along the direction dk. So if the function value decreases initially, then this is a descent direction. And to show that, we just need to show that the phi prime at 0 is negative. So it's pretty easy to do that. The phi prime of this at 0 is essentially just that. But assuming this, since we assume this is negative, then this definitely means that the dk is a descent direction. Okay, so we have done this a few times in the previous chapters as well. The second one, to show that since the dk is a descent direction, so we know that the function will decrease like that. Eventually it may increase somehow, but at least initially it should decrease. Because it's decreasing, then we know that the function, the minimizer must be reached at some positive value. Okay, so that's why the alpha k must be a positive. The step size, the optimal step size must be positive. The alpha k is optimal. So if we choose the alpha k to minimize the line search function, so that means if we have a function like that, if we find the minimizer here, which is alpha k, then the derivative of phi at alpha k must be equal to 0. So in that case, phi prime at this alpha k, the optimal alpha k, we can easily see that it's just this. And since alpha k is optimal, so by the first order necessary condition for the alpha k, we know this must be equal to 0. So these two together implies that the inner product of these two vectors must be 0. Okay, to show that the steep descent method satisfies the condition that the inner product of this is less than 0, we just recall that in the steep descent, the decay is just set to the negative gk. So that's, in this case, the inner product of the two is just the negative of the gk square, and that must be negative because gk is non-zero. For the Newton's method, the decay is set to this thing here. Sorry, it should be -1. So in this case, because the Hessian is, because the Hessian is positive definite, I think we assume that. Yeah, so we assume that the Hessian is positive definite. So in this case, this is a positive definite matrix, and the inverse must be also positive definite as well. So now let's look at the inner product of the dk and gk, which is this, and we substitute the dk into here, and then we get this. Okay, now you can see this is a positive definite matrix, and I have the same vector on both sides, and I have a negative right here, so that must be less than or equal to 0. But since gk is non-zero, this must be strictly less than 0, right? Since this must be a positive definite matrix. So for conjugated gradient method, our dk is set to that. So now, because in the conjugated gradient method, the gk is orthogonal to all the previously used search directions. So we know that the inner product of dk and gk, you just recall that when I multiply this dk with gk, but dk is this thing. So I just put in here. I will see that it's essentially just the inner product of gk with this, and then inner product of gk with that. But this will be gone. So that's inner product is this. But this will be gone since gk is orthogonal to dk minus 1. So this whole term is just gone. And then we have the negative gk squared, and that must be less than 0 as well. Okay, since gk is not 0. For the quasi-Newton's method, we set the dk to be negative hk, gk. So in this case, because the hk is positive definite, we will assume that it's positive definite, so that the inner product of dk and gk is equal to this, and again, because the positive definiteness of the hk and the gk is non-zero, then we have that is this is less than 0. All right, but finally, if our objective function f is a quadratic function, then due to the optimality of the alpha k, since alpha k minimizes the search line search function, so we know that the phi prime at alpha k must be equal to 0. So that means this equals 0. Okay, so because this is equal to 0, recall that for quadratic function, this is just the qxk plus 1 minus b. Okay, and so the qx plus 1 minus b, but this is exactly what the qk plus 1 is. So we put this in here, and then we try to solve for the alpha k, and eventually you can easily see that the alpha k equals this. Remember that you can do that only if you can see that the alpha k is multiplied to some scalar, okay? And then you can figure out the alpha k by moving this to the right and or moving this to the right, and then divide both sides by this, okay? Because this is a scalar, you can safely derive them. If you see something, the alpha k is multiplied to a vector or matrix, then you should be careful, okay? Especially when you're multiplying to a vector, then there's no way that you can divide that vector. So we don't have a vector, we don't have a division by vector in any sense. Okay, so you have to multiply, in this case, you have to multiply another vector so that the inner product of two vectors becomes a scalar, then you can safely divide it. Okay, otherwise cannot. Okay, so be careful about what you are trying to divide. Only if it's a vector you can divide, only if it's a scalar you can divide it. If it's a matrix, then you can take the inverse. But remember that the inverse, you need to make sure that the matrix itself is invertible. Okay, and the same thing here. Actually, to be rigorous, we need to show that this is a non-zero scalar. But that's easy to show because Q is a positive definite and D is non-zero, so this must be a positive number. So that's why you can divide it. Otherwise, you also need to, try to show that this is non-zero value that are trying to divide.